Okay, good morning. Welcome, everyone. So we have the pleasure to have today Germán Molpeceres de Diego. He is from the University of Stuttgart, and before he starts his talk, then I'll introduce him. For those who don't know him, Germán studied at the University of Valladolid, where he specialized in theoretical chemistry and computational chemistry. After finishing his undergraduate studies, he moved to Madrid to the Instituto de Estructura de la Materia, where he did his PhD titled Interstellar Dust Analogues, Structure, Survivability, and Physical Processes. After defending his PhD, he then moved to the University of Stuttgart, first as a postdoctoral researcher, and he has stayed there since. And right now, he is an Alexander von Humboldt Fellow. And Germán, so it's a pleasure to have you here. And whenever you're ready, you can start your talk.
Perfect. Of course, the pleasure is mine to be here, gathered with friends. And I'm really happy to present my research, or the research that I've been conducting during the last 2 years, titled Interstellar Surface Chemistry and Physics using Machine Learning Techniques. I must warn that I have tried to put everything in an understandable way and so on, but if anything is not clear, just please let me know and I will try to explain it better. Okay, so this is the outline of the presentation, and after a brief introduction of the astrochemical context in which I carry out my research, I will move to the normal theoretical tools in surface astrochemistry, and I will then discuss the machine learned potentials and the machine learned techniques that I employ. And after that, I will start to talk about different applications of these techniques to real problems in astrochemistry. And without further ado, let's start with the introduction. So for all of you that are not familiar with astrochemistry, everything starts with this cycle over here, which is the cosmic matter cycle. It tells us how matter traverses and travels around our universe. And of course, in every of the different regions that I'm portraying here, there is a different chemistry going on. It's not the same, the chemistry that occurs on a planetary system, such as our solar system, or the chemistry that can happen on the remnants of a dying supernova. But for astrochemists, and particularly to me, and computational astrochemists, the most appealing object in which we focus and we carry out our research are clouds. Clouds are regions in which a rich chemistry happens, and in particular, in dense clouds, for the idiosyncrasy of these regions, a rich organic chemistry happens. And why is this? Well, the reason is that the aggregation of dust on these particular objects leads to a filtering of the stellar ionizing radiation that does not permeate into the cloud, allowing for a buildup of organics that otherwise would be broken upon interaction with the ionizing radiation. This, as I said, allows for a buildup of chemistry that occurs in two different phases. In the gas phase, that constitutes 99% of the mass of these clouds, and is mostly made of hydrogen gas, and on top of ice-covered dust grains. Why ice-covered? Because at the temperature of these clouds that are as low as 10 Kelvin, most of the matter sticks to dust grains, forming and coating these dust grains with ices. Therefore, we have two different regimes, so reactions on the gas and reactions on top of icy dust. And in this talk, I will focus on these reactions and physical processes occurring on top of icy dust. And what an interstellar ice, or this icy dust, is? Well, it's a mixture of a core that is made out of silicates or carbonaceous material. This refractory core is inherited from previous stages of a cloud evolution stage, and several ices that can be accreted on top of it, that mostly are made up of water in the early stages of the cloud. But as the cloud progresses in time, we can find other components, such as apolar components, such as carbon monoxide, carbon dioxide, and eventually also methanol. So really complex and dirty ices. And it's important to mention that the composition of these ices is not homogeneous across the whole molecular cloud lifetime. With this introduction in mind, everything that happens on these ices to explain chemistry and physics can be summarized as a combination of 4 different processes that I present here. First of all, accretion or landing of particles on the surface, diffusion or mobility of these landed particles on the surface, reaction or formation of new particles on the surface, and desorption or return of the molecules to the media where they are eventually detected. In this talk, I will cover every of these different aspects from a computational standpoint, and particularly using machine learning techniques. Here, I deliberately omit other processes such as photo processes or cosmic ray-driven processes that are more complicated and subject of a different field of research. And ices on interstellar medium are a combination of crystalline ices, for example, the carbon monoxide ice, and amorphous ices. And from a computational standpoint, it's very different to treat ices that are crystalline, in where there are magic spots or positions on the surface that really represent the physics and the chemistry that can happen. For example, if a particle lands in this particular position, is the same as it lands in this particular one or in this one. So we have periodicity that allows us to cheaply study the different processes that can happen on this surface. However, most of the ices are found in an amorphous form. And in an amorphous form, there are really no magic spots for studying the physics and the chemistry. Here, the chemistry and the physics that can happen in this cavity is totally different than in this protuberance, for example. And therefore, it is very complicated to study the system efficiently. And I will go on how we do that in a minute. But I would like to convey why it is very important to study this kind of chemistry and physics. Well, so if we take a look at a model that predicts the abundance of several components in this cloud, so for example, the abundance of carbon monoxide, carbon dioxide, water, ammonia, and methane, we can see that if we disable completely surface chemistry, we have a profile that is absolutely different than when we toggle and we enable surface chemistry to happen. So we cannot understand astrochemistry without surface astrochemistry. Then let's move to how we usually treat this computation. So there are several approaches to treat surfaces and physical and chemical processes occurring on interstellar surfaces. Some of them are gathered in this slide and range, for example, to construct periodic slabs of different ices, representing a particular ensemble of water molecules in the case of water ice, to reproduce a particular binding situation with particles with the ice. We have also clusters, assuming that, for example, the main conditions for a binding of a particle on a surface comes from local environments. We can extract these local environments as study them. And we have mixing of classical models and quantum models to treat different regions of a system with a lot of accuracy and lower accuracy in order to create big models. But all these different ways of treating an ice that are, of course, very good for specific problems, fail in treating very big systems and models. And when we tried to apply our research to very big systems and models, we came to the conclusion that the best way of doing it was using neural network potentials or neural network models. Neural network potentials is another way of obtaining the dynamics and the forces and the energies of a system made of atoms, as for example, in an ice. But in this case, we are profiting from data science techniques in order to obtain these energies and forces. It has a series of advantages that are, for example, that these methods are very cheap once they are created, allow for an explicit treatment of thousands of atoms at the same time, and of course, they are able to simulate chemical reactions. So chemistry can be studied with these methods. However, using these methods requires a lot of knowledge on the systems that we are studying in order to be reliable. So starting a project using this kind of techniques requires a previous study on what are the interactions that are taking place on an ice. And on top of that, even though it's very cheap to use once it's generated, generating the neural network is an expensive endeavor that requires to be assumed before starting any new project. The general idea of this type of methods is to encode structural information, such as, for example, Cartesian coordinates. Cartesian coordinates are not really good for this kind of systems, but just for us to understand, we input some kind of coordinates here, and they are transformed into energies via linear transformations between the different neurons in the systems. The trick here is that the parameters that connect these input layers with the layers that transform into energies and eventually forces too are trained in known systems, in physical systems for which we know the answer on how the forces and the energies are. And therefore, the general strategy for these methods is going from a physical-based method, based, for example, on the Schrödinger equation, to data science methods that allow us for moving from systems of a handful of atoms, tens of atoms, to systems with thousands of atoms with an incremental increase in the cost of the calculation. So for example, here we have that it takes tens of minutes to calculate the energy and forces of systems of 80 atoms versus the time that it takes to calculate energies and forces of a system of several thousand, well, in this case, 1,200 atoms in one processor. And in particular, this is taken as time measures using a laptop computer. So we really can afford very expensive calculations once we have these kind of methods available. Once that is explained, I will go into detail into some applications in which these results that I'm going to be presenting here are just enabled by the use of these neural network techniques. And I will start with, in this diagram, these two processes here. So accretion or adsorption and desorption of particles. So what we are going to do is to simulate the collision of particles with the surface and how these particles eventually return to the gas. And the physics of these two magnitudes are defined by these two quantities over here. One, the rate of accretion that is obtained as a multiplicative expression of parameters that depend on the dash grain and on the gas, but mostly and most importantly, by a factor that modulates this kind of expressions. This is the sticking coefficient, which is the ratio of particles that remain bound to a surface after collision. So imagine it, a particle comes to the surface, and depending on the ratio that we have of the sticking coefficient, it will remain bound or not. This expression over here has not an analytic form and is difficult, very difficult to obtain and very expensive, and is only indirectly related with the binding energy of a particle with the surface. The desorption, luckily, is easier to obtain and is just an Arrhenius expression in which we have a pre-exponential factor and also a binding energy that represents the energy of the particle interacting with the surface. These are the two equations that we are going to solve by using machine learned potentials and by trying to take all these equations or all these elements of the equation from numerical simulations. I've been talking about the binding energy, and to illustrate what the binding energy is, because it's a central magnitude for the simulations that I'm going to present, let me tell what the binding energy is diagrammatically. So a binding energy is nothing else than the stabilizing energy that arises from the interaction between a particle and the ice. This binding energy comes mostly from electrostatic interactions and is positive, is negative by convention, which is that is stabilizing, and is represented as the difference between the energy of the particle and the ice minus the energy of the ice plus the particle at an infinite distance. Once we know the magnitudes, we can create the ices. And as I said, we can create ices that are realistic, that are big enough to study a lot of different outcomes with machine learned potentials. In this example, I show an ice that is created with 1,500 atoms, but in reality, we create 50 of these at different temperatures. And this number of atoms, 1,500, is in a stark contrast with the sizes that we can afford using physical-based models that are of around 60 atoms. With these realistic ices, we can further study the physics of particles on the ice. And for the nitrogen on the ice, the binding energies that I have been presenting present themselves in a broad distribution, in contrast with what astrochemical models usually use, that is only one energy representing the interaction of a particle with an ice. This shows the exact opposite, that is that a lot of different energies can be present on the same ice. Our results are in good agreement with the results of the average value obtained in the literature, showing that the nitrogen overall works very, very weakly with the surface. As for example, the ammonia molecule binds with the ice with energies that are an order of magnitude higher than in the case of the nitrogen atom. This overall weak binding makes nitrogen a good test case for what happens in other weakly bound particles. And what we did, therefore, was to obtain the sticking coefficient that I've been mentioned before to prove how these weakly bound particles interact with the ice surface upon collision. And for doing that, we studied a lot of different trajectories. We shot nitrogen atoms toward the surface in order to determine what are the different outcomes for many, many thousands of collisions of the nitrogen with the surface, ranging the angle of incidence of the collision, the kinetic energy of the collision, and also the impinging point on the surface. What we do after running this simulation is to count the number of trajectories that lead to a sticked event, so the particle remains on the surface, or to a bouncing event, or the particle returns to the medium. And we did this for around 1,800 trajectories per surface temperature, and we obtained simulations as the one I'm presenting here. So the particle lands and moves a little bit, eventually can desorb or can stay on the surface. This is done automatically for around 1,800 trajectories. So I must emphasize here that this is only possible and is enabled by the machine learning potentials technique. And after we have all the trajectories collected, it is time to start counting the ratio of trajectories that remain stick and the ratio of trajectories that bounce back to the gas. If we do that as a function of the incoming energy of the particle and the surface temperature, we observe that the ratio of particles that return to the gas phase is higher when the surface temperature is higher. So, for example, here 130 Kelvin, and the energy of the particle is, of course, high. This is in physical grounds, of course. However, this is also only taking into account the energy realm. If we go to the temperature realm, which is what astronomers like to use in their models, what we observe is that at the temperatures that are common for gases and surfaces in molecular clouds, we observe that most of the nitrogen atoms stay stick to the surface, thus confirming that nitrogen always remains on the surface at 10 Kelvin. And as nitrogen, many other particles, such as, for example, the oxygen atom or the water molecule, will always remain stick on the surface at 10 Kelvin. This is an assumption that was taken by astronomers for a long time, but this is, to the best of my knowledge, one of the first confirmations that theoretically this is a valid assumption. Once we know what is the outcome of the first moments after a collision, sticking or bouncing, it is time for the molecule to start, or the atom in this case, to start move on the surface freely, including, of course, the movement that leads to desorption after the collision. This is called desorption, and it takes place in long time, so after the atom or the molecule is thermalized on the surface. And in order to obtain which is the time that it will take for the molecule, and therefore the temperature that it will take for the molecule to return to the gas, we can monitor how frequently the molecule or the atom tries to return to the gas. We can do that with our simulations, and real long simulations are needed, and we can attain this, as I have been emphasizing, thanks to the use of neural network potentials. We can obtain this by monitoring how this molecule moves in the set coordinate leading to desorption over time. Combining this value that we obtain here, for this is the period, but we can take the inverse to obtain the frequency, and combining with the knowledge that we have with the binding energies and some other quantities that I won't go into detail, we are able to combine these two terms in order to obtain the temperatures at which we are going to expect the desorption of nitrogen, in this case, from the surface. If we do that, we obtain an average desorption temperature of 25 Kelvin, which, in comparison with experiments that present desorption temperature of 23 Kelvin, so that we have resolution, experimental resolution from our theoretical calculations in order to predict new physics and chemistry of particles landing on interstellar ice surfaces. This is, again, enabled by a huge sampling by using our techniques. We can really now attain distribution of quantities and unravel new surface physics on the interstellar medium. The next topic I'm going to talk about is the diffusion. And the diffusion is nothing else than instead of desorption, that is moving in the direction returning to the gas, the diffusion on the surface represents moving on the surface in order to scan it and find other reaction partners. Diffusion is way more tricky. It's way trickier than in the case of desorption or adsorption. Why? Because adsorption and desorption mostly depend on one particular site where the particle lands. So in this site, for example, the particle will try to desorb or stick, but it does not depend on the environment of the particle also. And in diffusion, this is not the case. In diffusion, the movement depends on the site where you start and the site where you end up, and also in the path that you take for making this trip. And therefore, the amount of events that are required for modeling diffusion are much higher than in the case of adsorption and desorption. Moreover, in the case of a crystalline surface, such as the one I'm presenting here, the diffusion is easier to treat because there are points of high symmetry and established paths for diffusion. This is not the case for amorphous surfaces, where we have random connections of different sites in order to lead to a movement of particles on top of the surface. Therefore, what we need is to construct from a given ice a catalog of connectivities of the different sites where a particle can be with all the other ones on the surface. For each one of them, we need the energies and the energies of the point that connect the elements on the catalog. And this is, again, enabled thanks to a fast and reliable sampling of the surface using machine learned potentials. Without entering into detail on how we obtain these graphs, let me tell you that we can now afford to really reconstruct the potential that a nitrogen atom experiences when moving on a surface. And by reconstructing this potential, we can identify pathways for diffusion and what are the pathways that an atom will take in order to move on a surface, which is what I said we need to model diffusion. If we superimpose this kind of potential energy maps on the real surface, we observe that the sites where the binding energy is lower, and therefore when the molecule or the atom is mostly attracted by the surface, are represented by blue points, and the forbidden regions, or the regions where the repulsive energy is higher, are represented by red points. And if we superimpose the real structure on this kind of maps, we see that these points, these blue points, corresponds to cavities on the surface that are present on amorphous ices, and the forbidden regions correspond to protuberances on the surface. This tells us that the diffusion on amorphous surfaces is generally slower than in crystalline ones, where these kind of cavities are not really present. But we can also focus on extracting numerical quantities, not only qualitative conclusions on the diffusion. And for that, what we can obtain is the diffusion energy, of great help for astronomers in order to model the evolution of particles on surface. But also, what is the average length of a diffusion event? These two ingredients that we can take now from our simulations can be used to really model the macroscopic diffusion on a surface. And if we compare this with from the value that we can obtain from our simulations and the value that we obtain by employing an analytical Arrhenius expression, we observe errors of almost 18 orders of magnitude at low temperatures. This is, of course, due to the fact that in using this kind of expression, assume an average value. And in the case of diffusion, we have observed that using the whole distribution of different ways of overcoming different diffusion paths is fundamental in order to capture the physics of diffusion. Here, in this graph, I saw in dotted points, in dotted line, the values using the average value here, and also using the whole distribution. And you see that the deviation is dramatical at low temperature. This is an inverse temperature units. But not only the difference between average values and considering the whole distribution is important in order to realistically model diffusion. Another thing that is fundamental is the number of particles that are coexisting on the surface at the same time, which is a requirement that interstellar ices have. So they are dirty ices in which many particles are moving that deviate from the case in which one particle is the only one moving. This happens because several particles moving at the same time will occupy sites of cavities on the ice, allowing to other particles to move freely on the surface, increasing the diffusion and giving us hope that really diffusion can happen in space, but only when coverage of these ices is high enough. Coverage is something in which experimentalists are really concerned, and it's really fundamental to report the coverage of your ices in order to really understand what is going on in diffusion. After that, I've been talking about physics, so diffusion, desorption, and adsorption, and now I will talk about real chemistry happening on the ice and using these machine learned potentials. A reaction is what happens when two diffusion particles meet, in which a new chemical species is formed. And I will focus here on how the pH radical, so one of the simplest phosphorus-bearing molecules, is formed on interstellar ices. But before that, let me introduce some new concepts. One is reactive desorption and non-thermal diffusion. These two concepts are illustrated in this simulation, in these animations, in which what I'm trying to convey is that when a molecule is formed, a huge amount of energy is released. And this huge amount of energy can be employed in many different things. One of them, desorb very, very violently, or diffuse a lot in the aftermath after the formation of a molecule. There are other agents that are able to trigger these kind of events, such as, for example, photons, X-rays, or cosmic rays. And there are experts in CAP in simulating and seeing in the laboratory these kind of effects. Why I chose pH as a test case for the reactivity using machine learned potentials is because several reasons. So very recently, it has been proved that the phosphine molecule is able to undergo the reacting desorption events that I've been talking about. And since the pH molecule experiences lower binding energies and a higher reactivity, it is expected that this molecule will also experience a higher degree of chemical desorption, which is very important because pH is not yet detected in cold regions, and pH is very, very reactive. So it can undergo chemical conversion to other phosphorus-bearing molecules. So understand the fate of this molecule in space is fundamental in order to uncover how phosphorus evolved in it. And now I would like to show some trajectories that are produced from this study. So what we do is to place a hydrogen atom close to a phosphorus atom and observe and leave the system evolve. And here I present a trajectory that leads to desorption. And what you see here is that the atom recombines with the phosphorus atom and starts to be rotationally excited until it collides with another water molecule. And by momentum conservation leads to a desorption of the molecule to the medium. We have uncovered the mechanism in this particular case for chemical desorption, and is the interaction of the hydrogen atom with another hydrogen atom on the surface, implying that the more hydrogen atoms on the surface are, the more effective the chemical desorption event is, highlighting the importance on the morphology of the ice in the desorption, or the amount of hydrogen atoms that are readily available for this kind of interaction. But of course, we can also study some energetic parameters from these kind of trajectories, and we can analyze how the energy of the ice increases after the formation of the molecule. This is in orange, and as you can see, for a reactive event, for a desorption event, there is almost no transfer of energy from the molecule to the ice, and most of the energy stays on the phosphorus hydrogen, so pH molecule that remains the surface excited. But however, this is only a rare event, doesn't happen so often. The most normal outcome of a reaction is that the molecule stays on the surface and starts to diffuse a lot in the time frame of the simulation. When the molecule does that, it starts to move following a given path, similar to the one that I've been presenting before in the study of diffusion, in which in every movement, the molecule inoculates some energy into the ice, slowing itself in the process. So what we observe is that in the time frame of the simulation, most of the energy of the reaction is captured by the ice, which is presented here again in the orange line, and the energy of the nascent molecule starts to decrease. This means that after some time, the molecule will relax on the surface and it will start to move thermally very slowly, as I presented before. But not only that, these are not the only things that we can study using these techniques. We can take a look at almost everything. We have total control to study the dynamics of a nascent molecule using machine learning potentials. So we can, for example, take a look at how the internal vibrational energy evolves over time, which allows us to give information on what is the expected vibrational state of this molecule when it leaves the surface after chemical desorption. We can also take a look and decouple the internal energy that is inoculated into the molecule after the formation into the sum of translational energy and internal energy. And this allows us to really rationalize how this molecule will move on a surface in different binding sites, for example. This is too technical, I am aware of it, but the main message here is that we really have now total control on the dynamics for studying reactive events, which is something that was not possible, for example, 5 years ago. And this is in turn my take-home message. Machine learning potentials really allow us to study most of the chemistry that can occur on top of interstellar dust grains, which really open new avenues for understanding what is going on in the surface of interstellar grains, and it enables a better understanding on the processes that form organics in the interstellar medium. Of course, there are ways to improve these kind of techniques, and among these ways, I'm aiming particularly to expand to our domains to photoprocesses or other energetic phenomena, such as the one that I studied in the Center for Astrobiology. With this, I conclude, thanking, of course, my collaborators around the world and the people that have helped me during this project. Thank you very much.
Thank you, Germán. Thank you very much for this nice talk. So I think we are going to open the session for questions. So if you have any questions, and then you can either raise your hand or type them in the chat, and then I'll read them loud. And what I'll do is I'll start with a couple of questions so that we let people have some time to write them their questions or just raise their hand. So I have 2 or 3 questions. So from your new method, no, using these machine learning techniques, so what you're showing is that there's a distribution of binding energies, or there's also a distribution of desorption energies, no?
Yeah.
So I was wondering whether, so does that distribution represent the reality? So if you have the possibility to go to the lab and then measure those binding energies, so would you find that distribution of energies?
Yeah, that's an excellent question, actually. So yes and no. So the distribution that you find in the lab is narrower. You find a distribution, definitely, but it's narrower. Because one good thing about this kind of theoretical approaches is that they isolate specific processes. So when I study absorption, I only study absorption. It's absolutely decoupled from diffusion. But in a lab, what you have is a combination of all the processes that are occurring. So you cannot disentangle when you have diffusion and when you have desorption. In a lab, what you will observe is that most of the particles diffuse before desorbing. So that makes the distribution narrower, because at the end, the outliers of our distribution are filtered out by the experiments normally.
Okay. And then if I may, then I'll ask, and Andres, I'll ask another question. And then for the case of pH, then you have shown that there are 2 possible outcomes, if I understood correctly. That you have the reaction of P plus H, and then that leaves the surface. And then there's this other possible outcome in which you do the reaction of P plus H, and then it diffuses on the surface, losing energy in favor of the surface.
Yeah, exactly.
Then how do we implement this in chemical models? So is there any way of quantifying what fraction of that reaction gives you pH back into the gas phase, and what fraction stays on the surface?
Well,
because that's what we are interested in. So
yeah, of course. Yeah, of course, I know.
And
the main problem is that this, what I have shown for pH, only holds for pH, really. So chemical desorption is something that is so dependent on the system that it's very difficult to generalize. How I would implement this into chemical models? Well, just having 100 people taking a look at every possible system that is of interest and making a lot of simulations that are very expensive each, in order to obtain a number of the ratio of particles that leave and not, and hard code that into the models. No expression whatsoever, just plug the number for every specific system. It's such a difficult way of working that in reality, I don't see in the near future a way of implementing this into astrochemical models. And it's really a challenging task that we should take at some point, yes.
Right. Okay. Thank you very much.
Thanks to you.
Juan Garcia.
Hi, Germán. Congratulations. Great work. Very beautiful work. It's just a curiosity. That's trajectories that you have simulated. The initial conditions, what are? Because if we are simulating an ice, the internal energy of the ice should be very low, and I saw that there is a lot of kilojoules of energy in that graph that you've shown. So if for simulating a reaction at 10 Kelvin, what is your initial conditions? That is.
So I understand your question. So what you're meaning is that the beginning of the ice is in this point, right? Yeah. So the ice is at 10 Kelvin. However, this is the energy that an ice of several thousands of atoms has at this temperature, at 10 Kelvin. So every particular molecule has a has 10 Kelvin, so it's has very, very few internal energy. But of course, since we have so many atoms, at the end, everything sums up, and reaches this energy. But the initial conditions are 10 Kelvin for gas.
Okay.
So if I would plug here the energy per atom, of course, it would come to this point more.
Yeah, okay. And then just another one. The size of the system, how could we increase the system? For instance, I don't know, it's a lot, but imagine 10 atoms in these trajectories, or is too much?
What do you mean by 10 atoms during the,
so system,
10 reactions?
Yes, a system that is, for instance, a bimolecular reaction on the surface of this size, for instance, of this size. Could we do that kind of studies with a 10 atom system on this surface?
Yeah, so it is possible, definitely, but the most complicated the system is, the most difficult is to train the neural net. I haven't entered into details on how I construct these potentials, but in principle, everything is possible. That doesn't mean that everything is viable. So it would require a lot of calculations in order to cover the space of 10 types of atoms. Possible, yes, definitely, but it requires really, it's complicated, I would say.
Okay, so you build the potential for your system, and then put it in the network. So it's like creating like a molecular mechanics code.
Similar.
But yes, but so you should do it for each system you are going to study.
Yes, but with one advantage, and is that we can reuse what we use between projects. So for example, the part of the water that I have here can be reused to another system in which I will use water, right? So in reality, if I want to study here nitrogen instead of pH, for example, NH, I would need to increase the training set, but for the parts that include the nitrogen, the parts that include the water, as long as the theory level is the same, can be reutilized. So at the end, it's something funny. And the cost of the project decreases over the number of projects.
Yes. Okay. Thank you very much, Herman. Congratulations again.
Thanks to you, Juan. Thanks to you.
Thank you. So we have another question from Andres Mejias, who says, very interesting talk. I was wondering what kind of neural network you use for the estimation of the energies. Thank you. Yeah.
So these are feed-forward neural networks, but that doesn't say a lot. So what we use are architectures of deep neural networks. So we use on the order of five. These studies, I think they are done with 512 neurons per layer using, if I'm not mistaken, 4 layers. So it's deep for chemical standards. And also we use an in-house version on how to encode the structural information, which is called Gaussian moment neural networks, in which the structures are converted to Gaussians. So the molecular environments are converted to Gaussian functions that helps a lot into the different processes of passing information from the beginning of the neural network to the very end.
Okay, thank you. Then we have another question from Santos. He says, thanks for the talk. I have a general question. Could it be possible to use these machine learning techniques for surface adsorption processes at room temperature? Or in that case, temperature is simply too high?
No, it's even easier. Everything that involves high temperatures makes it easier to sample many other different outcomes. The problem that happens at low temperatures is that in many cases nothing happens. So you need to really take or you use, for example, amorphous surfaces that are not what you would expect at room temperature. At room temperature would have crystalline ice or crystalline materials, right? So actually, most of the people starting to employ this kind of techniques of machine learning potentials are using them for studies at room temperature and simulate. For example, this is very much used now on material physics. So yes, definitely possible. And actually, I would recommend it now to start to do this kind of things.
So would crystalline ice make the calculations faster, or?
No, not faster. At the end, everything is determined by the size of the system. But a crystalline ice is much easier to model, really, because you don't have as many different arrangements as you have in an amorphous ice. So the information that you require to create a reliable neural network is low.
Okay, thanks so much. Let's see, are there any other questions? No, I don't see any other question. So, well, thank you very much, Germán.
No, thanks to you.
Great talk. And hopefully in the future you can come and then visit CAP, then that would be great. Yeah,
I would be delighted.
Yeah, I'm going to stop recording.